automating disk and memory evidence collection in AWS.
Hey everybody, just give me one sec while I share my screen. All right. All right, so hi everybody. My name is Ryan Tick, and with me today I have Vaishnav Murthy also on the line. He is a co-presenter on this, and we are excited to talk to you today about how we're automating disk and memory evidence collection in AWS at Goldman Sachs. But a little bit about us first. So at Goldman Sachs, we are part of what we call our Sky team. And our Sky team is responsible for securing the firm's use of the public cloud. And currently we're focused on AWS, and we're going to talk to you about this solution that we've developed for capturing disk and memory evidence on EC2 instances. And this is a large firm-wide initiative that we've been focused on now for, I think, about 8 months. So we're excited to talk to you about that today. And we have a couple industry standard certifications, if it means anything to you. We hold a lot of SAN certifications, as well as all of the associate AWS certifications and the security specialty certification as well.
Yeah, thanks, Ryan. And prior to Goldman, we were both consultants for KPMG in the cyber response practice. So definitely shout out to any of our former KPMG colleagues that may be watching this talk right now. And before that, we were both graduates, computer science graduates from the University of Notre Dame. So basically joined at the hip and the same person. My name is probably just a little harder to pronounce than Ryan's. And you want to give a fun fact about yourself?
Yeah, so we try to make this a little personable, try to keep you awake late in the day. So a fun fact about me is that I was born 4 months premature. So I probably weighed less than the laptop that you are watching this presentation on. I weighed about 1.5 pounds when I was born, and now I am about 6'2" and fully healthy. So thankful for that.
Yeah, and my fun fact is, on occasion I do open mic stand-up comedy, but I assure you that this talk will not be funny, at least on purpose.
And with that, so we've included our emails here. We're going to include a lot of contact information at the last slide of the deck as well that you can note down and reach out to us for any questions or feedback. So with that, we wanted to give a little overview of our solution.
So to contextualize the problem statement we were trying to solve with our solution, the problem we were trying to tackle is one that many companies have to face. How do you automate the collection of disk and memory evidence of compute resources in the cloud? And this task was further complicated given the scale of our firm's footprint in the cloud. So our firm has 3 AWS organizations with over 3,000 accounts that we needed to factor into our solution. And so we needed a scalable, auditable, and repeatable process to satisfy our stakeholders, which are both business units that were running hugely profitable workflows that could not be interrupted, and our legal and risk department that wanted to ensure that any process we implemented adhere to the applicable regulations with us being financial services firm. So before moving on to our solution, we just wanted to have a quick note about AWS organizations, as this is pretty key to understanding our solution. So AWS organizations is a service in AWS that helps you centrally manage billing, control access, compliance, and security, and share resources across your AWS accounts. And what this allows you to do is effectively segment resources across various business units or functions. So your production business units would have their own accounts, your security team would have its own accounts, and so on and so forth.
So as we start to dive in here, at the heart of our solution, we have AWS Security Hub. And if you're not familiar with Security Hub, it is a single place that aggregates and prioritizes what Amazon calls security findings. And it does that for multiple AWS services, and I have that kind of on the left. And it also integrates with third-party solutions and AWS partner solutions as well. So when designing our solution, we need to be able to accept 2 main use cases. or two main sources as part of our use case. And these are identified as our two feeds. So we have our automated sources on the left, and on the right side, you'll see we have some manual triggers. So if we look on the left real quick, the automated sources, we need to be able to trigger our solution automatically. And this comes from a variety of tools, such as cloud native tools, as we talked about, and technologies like Amazon GuardDuty, Inspector, and Macy, which you may have heard of before. But we can also plug in with third-party tools such as your IDS, your IPS, or your EDR. And then on the right side, the second use case was for a manual trigger. And this really boils down to the fact that no one tool can catch everything. You know, we're big on Amazon. Amazon has a great selection of products and services out there. But we also use outside vendors, and we get outside feeds as well. So if our security and incident response team suspected that an instance may be compromised, we wanted to provide them a means to kick off our workflow without having to, you know, page or call me or Vaishnav in the middle of the night, because that's not fun. And this is where the manual input comes in. So for example, you know, if you receive a third-party notification that an instance has been compromised, maybe it's sending out anomalous or malicious network traffic, and it's trying to brute force other hosts, or maybe there's a pen test finding that you want to investigate further. So that's why we allow for this manual trigger.
So the outputs of our disk and memory collection process that we want to talk about, you know, is as follows. For disk, we collect a full DD image, which is a bit-for-bit copy of each volume attached to the affected instance. The reason we do that and not, you know, triage collection is to satisfy the regulatory requirements that we need to adhere to being a financial services firm. The second thing that we capture is the DC3DD log file. So DC3DD is our collection tool of choice, and this log file basically contains the hash of the DD image, as well as start and end times of the collection process. So that leads into the auditable portion of this this workflow. And then thirdly, we capture custom collection log files. So basically timestamps of all the commands that we run on our collector VM EC2 instance. You may be asking what is a collector VM EC2 instance? We'll talk about that in a few slides. And so for our memory, we do a full memory capture in the raw format. Basically, for ease of use with Volatility, which is our memory forensics tool of choice. And if the memory capture is from a Linux EC2 instance, we create the custom memory profile on the fly, which allows us to parse the memory image in Volatility. And this custom memory profile consists of the dwarf dump and system map files, basically containing, you know, kernel symbols that allows Volatility to parse the memory dump. And then just like with disk, the disk process, we also collect, you know, custom log files, which details the timestamps of all the commands run, their status, whether they succeeded, failed, and their timestamps again for auditability purposes.
So we're about to deep dive real quick, and we'll be conscious of time here, but we wanted to kind of put forth some main takeaways before we go forward to keep us all grounded during the talk. So the first point I want to emphasize is there's a lot going on behind the scenes than you may originally think. So for our solution specifically, we're dealing with 3 different AWS organizations that total over 3,000 accounts. So not only that, but in all those accounts, we have various types of EC2 instances, and they may or may not be using some form of encryption or have access to, you know, the internet, network connectivity, or logging. So our solution really had to consider cross-account access, EBS and snapshot encryption, sharing KMS keys and SSM documents, and some access logging as well, whether that be from S3 or CloudTrail or CloudWatch logs, etc. So that's point 1. Point 2 is pretty self-explanatory. You know, if you automate a task correctly, your mean time to respond, your cost, and your error rate are likely to be reduced. And the third point, so our solution scales with ease. Again, this was something that was really important to us as we developed this in our developer accounts. But if we're going to deploy this across 3 orgs and 3,000 accounts, everything needed to scale easily. And using a lot of cloud native technologies, especially with AWS, allows for that. So all of our resources are spun up and used dynamically. And when they're not being used, you know, they don't exist. And this is really important as we look at point 2, because this helps you keep costs down. And lastly, so we wanted to do this in the most secure way possible. So being a financial services firm, our risk tolerance is probably a lot lower than yours. We're heavily monitored by regulations, and all the lawyers will tell you, and I agree that's a great thing. So what our solution leverages is what we call VPC endpoints, and it's able to send all of our traffic over the AWS backbone network. So none of our traffic is being sent over the public internet. Our risk and legal team wasn't even comfortable with us sending traffic over HTTPS in some cases. So those are our main takeaways. And now we're going to deep dive into the disk portion of our collection process.
So before going further, we thought it might be helpful to describe what often exists in this space, mainly to explain how our solution is different and why we've taken a different approach. Much of the literature and documentation while we were developing this process that we researched on best practices in this space seemed to suggest the use of a very permissive investigator AWS principle, be that an IAM user or role, and a forensic workstation AMI, like a fifth AMI, to be present in each account, for your organization's security incident response team to use to collect evidence and perform investigations. However, this doesn't really fit our use case because, number one, it doesn't necessarily follow the principle of least privilege. The investigator role in many of these documents requires the permission to launch resources in the target account, which if an attacker exploited, it could be used to spin up malicious resources, which we definitely did not want. Our risk appetite did not allow for that. And secondly, this approach could take up resources in a production account, which again, was not acceptable to us because, for example, by default, you can only have a maximum of 20 running EC2 instances per region. So if your security incident response team requires, having 1, 2, or 3 forensic workstations running while performing analysis within a production account, this could be taking up resources that a production workflow, which scales up and down on demand, might need. So we wanted to have our solution be as least intrusive as possible. So instead of using this approach, we largely operate in our own security account within the organization. This is why we wanted to introduce the concept of organization. So we have our own security account, which our team completely owns and operates, and we don't have to share with any product team. And for cross-account access that is required, we use least privilege roles that only allow creation and sharing of snapshots. So this way we reduce the risk of profile of our cross-account access.
All right, so as we look at the process that exists before automation, and I swear that putting together this slide was more difficult than actually implementing our solution in AWS with all these pictures and getting them to align. But there's kind of a lot going on here manually that we had to go through. So all of our notification sources are integrated tightly with PagerDuty. So if something goes wrong, or if AWS thinks something goes wrong, shout out to GuardDuty, then we get paged in the middle of the night and we have to respond. And no one enjoys getting woken up in the middle of the night. And this is a very manual process. So we would have to deal with a lot of cross-account access, taking encrypted snapshots and sharing the encrypted snapshots cross-account. We'd have to be able to decrypt those snapshots for analysis. And then we would have to actually jump through our Bastion host or our jump box onto our analysis instance before we can even really start the collection. After the collection was done, we'd have to make sure that all the proper cleanup was also taken care of as well, not only in our security account, but also in the target account where where the compromised instance lives. And depending on the size of the EBS volume that was attached to that instance, it could take a while to collect a full DD image and output it to an S3 evidence bucket. In our experience, this likely takes a few hours if you're dealing with a large EBS volume. And then once it got us uploaded to S3, we'd have to make sure all the hashes matched and everything was verified there. Otherwise, we'd have to redo it. So another point I want to clarify here is that and kind of before we automated everything, our infrastructure was always running. So our Bastions and our analysis instances were just always spun up, and they just always lived in our security account. And that was great. We were paying for resources we weren't using it all the time, but the trade-off was, we had speed on our side. So we could leverage these a little more quickly as opposed to having to spin them up. But it definitely wasn't the most efficient solution. So that's where some of this automation comes in.
So here's our diagram detailing, the workflow of our automated process for disk collection. But before going into this, we just wanted to make a quick note about AWS Security Hub, because this is a sort of a newer service that some of you may not be aware of. So we use AWS Security Hub as the repository of our security events within each organization. And this is for a couple of reasons. Firstly, AWS Security Hub enforces a common format for findings from all the disparate sources that we have in use. So the sources that Ryan was talking about, you know, the AWS native sources, as well as third-party partners and manual inputs. AWS Security Hub enforces a common finding format, which is the Amazon Security Finding Format, which reduces the ETL that we might have to do. And secondly, AWS Security Hub follows what we call a master member subscription model. So basically, if a finding is inputted into a member account, which is basically all our production accounts, the finding is automatically replicated to the AWS Security Hub master account, which is our security account. So therefore, our security account has a consolidated set of findings from across the organization that we can act on. So once we get the finding into Security Hub, our automated process really kicks off. So, you know, trigger from guard duty or a third-party integration or a manual input gets fed into Security Hub in the production account, the monitored account, and then due to this member-master relationship, the finding replicates into the security account, which kicks off a CloudWatch event. And we have a CloudWatch event rule, which picks up the event, and then triggers our forensic pipeline step function, which we will talk about in a little bit. So our step function really coordinates the cross-account access into the monitored account, which then creates a snapshot of each volume attached to the affected EC2 instance, then creates an encrypted copy of the snapshot using a KMS key in our security account, which allows us to share it back with our security account. Once we have access to the shared snapshot in our security account, our step function spins up a collector VM, which again, we will go into in a few slides, which then mounts the volume, streams a DD image to our evidence S3 bucket, and then shuts itself down. It's basically on-demand spins up and spins down. And then lastly, we want to talk about this in a few slides as well, but we have an AWS CloudWatch logs agent installed on our collector VM EC2 instance, which really allows us to monitor progress of our collection process.
So here is our disk collection step function at a high level. And Vaishnav went over a lot of kind of the parts of this step function. But again, so step functions are a powerful orchestration tool by AWS that allows for the creation of serverless workflows. So we use a step function to coordinate the different lambdas involved in the disk collection process. Each state in our step function calls a different lambda, and these lambdas live in our security account. And if needed, they're able to assume a role into the target account to accomplish their goal. And yeah, we've already gone over a lot of this at a high level, but there are a few things that may not be too obvious. So the first one is error handling. Step functions allow us to set a very strict retry policy. So if we want to retry a state a certain number of times with a backoff interval specified between retries, we can customize all of that pretty easily. Related to that, so a design consideration that we made was that we wanted to decouple everything as much as we could. And this really follows some AWS best practices. So as you may or may not know, lambdas will time out after 15 minutes. So for example, we looked at the first lambda there. If we try to create a snapshot and simply just have that all be done in the first, in one lambda, it may time out after 15 minutes. So instead we've decoupled it, where we kick off that create snapshot API call, and then in another lambda we call, and we just query that snapshot ID. And that's a lot easier to check. As long as you just check and make sure that it has the state of active, then you're able to work with it. And that helps us, you know, with the native retries of step functions as well. And then the last step of our step function, so we actually spin up our collector VM, and that's the VM that's going to run DC3DD on the target volume and output it to S3. So we'll talk to you a little bit about that now.
So many of you might be wondering at this point what this collector VM we have been talking about is. What it is essentially an EC2 instance that we use to perform the collection process. It's created from a custom AMI that is based on the Amazon Linux 2 AMI. How we create it is a lambda that is triggered via a scheduled CloudWatch events rule that basically updates the packages installed and stores the new custom AMI ID in an SSM parameter that is read by the forensic pipeline step function. And in this way, we're able to ensure that every time our step function runs, it's using the latest and greatest collector VM AMI. We also ensure that our collector VM has the least attack surface area that is possible to perform our workflow. So it's deployed in a VPC without any internet access and has a restrictive security group with no inbound rules and no SSH key associated with it, which basically prevents unnecessary access. So the process that our collector VM follows is basically the last Lambda in our step function spins up a collector VM instance with the volume ID assigned for it to collect as an environment variable. And this is done using the instance user data. User data also runs a script that attaches the assigned volume to the instance. This attaching of the volume triggers an in-cron job that runs DC3DD on the attached volume and streams it to the S3 bucket. So quick note about in-cron. For those of you who may or may not know, in-cron is a Linux service that functions similarly to a cron job, but allows you to trigger actions based on file system changes. So what we do is we have our in-cron job monitoring the /dev directory, and when a volume gets attached, a block device gets created in that directory and then gets picked up by our in-cron job, and then which runs DC3DD on it. So while DC3DD is running, it creates a collection log which shows the progress the collection process, and this gets streamed to CloudWatch logs basically for debugging purposes, because as I previously mentioned, we basically do not allow any hands-on keyboard access to the collector VM. So if we want to monitor what's really going on, if there's a delay in the collection of the DD image, we're able to do that using CloudWatch logs. Then once the DD process is complete, the EC2 instance self-terminates. So that again goes back to our requirement about scalability and elasticity, which is really an AWS best practice.
So yeah, if you're not familiar with CloudWatch logs, I definitely recommend digging into it a little bit and taking a closer look. But yeah, as Vaishnav said, this was a necessity of our solution because we have zero access to this box. We needed to stream all of the logs off this box for analysis, for debugging, etc. So if something goes wrong or we wanted to track the status of a collection, these logs are great to have in a CloudWatch log group. So we have a custom config file on our collector VM instance, and we gave that instance profile basic CloudWatch log permissions so that it could write their logs out to a CloudWatch log group. And this is all done again via a VPC endpoint. So it's not going over the public internet, it's going directly over the AWS backbone network. And you'll see on the right side here, it may be a little small, but it shows a lot of cool things such as bytes copied, collection speed, and time elapsed. And additionally, we also are stringing a lot of standard logs off that instance that may be helpful from a debugging or a security standpoint as well. So we have pro tips now, and the point of this section was to share with you kind of some lessons learned that we learned as we were developing the solution. These caused a lot of headaches for us, and we're trying to save you some pain if you were to try to recreate this solution.
So our first real pro tip is we wanted to make sure that our collection process is as efficient as possible. And part of that really is to make sure that independent tasks within the collection process are executed in parallel. So for example, if an affected instance has 5 or 6 volumes attached to it, it really makes no sense for the snapshots of those volumes to be taken serially, which is like one after the other. So we accomplished parallel snapshot creation and attaching of volumes to the EC2 instances and so on and so forth by leveraging multi-threading in our Lambda. Basically, each thread handles processing for a single volume. So you may ask, why not just use concurrent execution of Lambdas instead? That's another way of, facilitating parallel execution, which is a great question. But we wanted to limit the hit on our account's Lambda concurrency limit, which is a consideration we need to make within AWS. So even though we own and operate, our security account where all this is running, there are a lot of other workflows running in the account as well, which involve Lambdas, and we really didn't want to encroach upon that concurrency limit if we didn't have to. So we decided to do multi-threading. And in a similar vein, we basically assign a collector VM to be spun up per volume to be collected, because it doesn't really make sense for the volumes to be collected serially, one after the other. So we make sure that as soon as we're ready to start collecting volumes, a collector VM is spun up per volume, and then we're collecting all of that parallel. The second consideration is one that many security teams have to deal with, which is, do we collect a full disk image or do we do a triage collection? In our specific use case, we focused on a full disk collection because of the regulatory requirements in our industry. But however, triage collection could very well be appropriate for your use case. For us, we kind of like try to do the best of both worlds. So we're leveraging CloudWatch logs to stream relevant log files from all our EC2 instances in production to CloudWatch logs. So basically, we have access to log data from our production instances to get some quick wins before DD images have been completed. Third thing is streaming evidence directly to S3. This is really important to us because we did not want to have to use intermediate storage, and streaming directly to S3 really quickens the process by which the disk image is made available to the forensic analyst.
So for the last couple points here, again, being a financial services firm, auditability was really crucial for us. So we're leveraging CloudTrail and CloudWatch log groups to track every API call that's made. Our solution also outputs custom log files to CloudWatch log groups, so we know what's being performed at all times with timestamp. And again, it's done entirely over the backbone network using VPC endpoints. The next point is that, cost versus collection speed. So in our testing, we found that an M5A class instance makes the most sense for us because it provides a high max network work bandwidth. So when we're streaming the data directly, we don't take a hit on that, and its cost was relatively cheap as well. Going down to the last 2 points, so instance stored data. If you're not familiar with it, basically this is data that upon shutdown just gets deleted, and this is currently not captured in an EBS snapshot. Our process right now does not make use of any instance stored data, so we don't collect that currently, and that's not as widely used. Actually, AWS recommends trending away from that. But we do have a prototype process in development, and that's basically just to execute DC3DD directly on this data via an SSM document, and then just similarly stream this data to S3. Order of operations really matters here. So as we talk about collecting memory, this is something you'll want to do after, as it will change the contents of the disk and the memory. And lastly, in order to ensure that we have consistent hashing, when we convert these snapshots into EBS volumes and attach them to our collector VM, we make sure that they're HDDs instead of SSDs, because SSDs use wear leveling and trimming, and as you may know, you'll get an inconsistent hash, or you have the opportunity to get an inconsistent hash before and after collection. So we really wanted to cross all of our T's and dot all of our I's and make sure our hashing matches. So as we move on now towards memory collection, our deep dive, we have another pretty picture as before.
Yeah, and so similar to our disk collection, our manual process was very, very painful. And specifically for memory, it involved ad hoc access of the affected instance, which again would often be a production instance. Then we would proceed to download and deploy tools from an S3 bucket to perform memory collection, then execute the memory collection and perform a manual cleanup. So once we collected the memory dump, we'd stream it to, or copy it to S3, and then have to delete our memory tools off the instance. So in addition to this being a slow and manual process, it would also contaminate evidence because you are downloading tools to, live instance. And in many cases, we also couldn't control the VPC where this affected EC2 instance was running. So often it had to be modified to allow access to S3, which really has the potential to affect an existing production workflow, which again is, risky and a problem no one really wants to deal with. So we decided to sort of streamline and automate this.
So after automation, our memory collection workflow is similarly triggered from a security hub finding and orchestrated by a step function. Again, our Lambda will then assume a cross-account role with access to SSM, which is used to execute memory collections. One thing up front we had to do is a lot of planning here. We wanted to really limit the corruption of the memory evidence that we're going to gather from all these EC2 instances. And in order to do that, we had to make sure that we controlled the AMIs that we allowed our end users to launch within the environment. We do that because we wanted the AMIs to contain our memory collection tools and some native AWS tools as well, like SSM, like the SSM agent. Because if we're trying to get an exact point in time memory capture, the last thing that we want to do here is really change the instance if we can avoid it. So we don't want to go ahead and grab those tools from an S3 bucket, download them, and then do our collection, because that may contaminate some evidence. Next, and we'll show this in our step function, we're performing a series of checks on the affected instance before we collect memory. And this was a lot more necessary for us to do with memory as opposed to disk, because anytime you play with memory, you could easily blue screen or cause the system to reboot or shut down if you do it incorrectly. So the first check we do, for example, if the instance isn't replaceable, meaning if it's not in an auto scaling group, currently we're not collecting memory because again, we're planning for the worst here. So if we were to brick a machine when we try to collect memory and it went offline, if it was in an auto scaling group, the load would shift to another instance within that group, and then another instance could also be spun up if necessary. So that was really important to us too. But we do allow for the cert team to set what we call a force flag in their manual trigger. So if we've gotten approval on everything on our end and we want to force a memory capture, we can still do that. And lastly, this could be a talk on its own. But since we're not comfortable at Goldman streaming things over the public internet, we have to use VPC endpoints. And S3 and Dynamo VPC endpoints are special endpoints. They're called gateway endpoints, and they're the only two services that use gateway endpoints. If you don't know, gateway endpoints require modifications to the route of the subnet that the instance is hosted in. So we do a lot of dynamic checks on our end to see that if we can make that modification without breaking anything. We need to make these modifications to make sure we can stream memory directly to S3 over the AWS backbone. But we do need to make changes here. Again, this could break production workflows. So if we can make these changes using our dynamic checks, we figure that out, we'll go ahead and do the collection. If not, we'll kind of pause at this point and we'll hold for some approval. So we'll work with my management and different business units and data owners to see if we can go ahead and collect memory from that instance. And once memory is collected, we do a little bit of the remediation. We attach a restrictive security group to that instance. And the restrictive security group allows nothing. It allows no inbound, it allows no outbound communications to that instance. And then we actually go ahead and we suspend that instance. And a few of you may be asking, why would you suspend the instance if you've already attached a restrictive security group that doesn't allow anything in or anything out? And we're big believers in test verify. So it's important to note that if you attach a security group to an instance, even if it has no inbound and no outbound rules, traffic can still be sent from that instance. So this is something you may want to play around with. And if you don't believe me, you should definitely look up tracked versus untracked connections in Amazon. But yeah, even if you apply the restrictive security group there, not allowing anything, communication, specific types of communications, specifically tracked connections, can persist for up to 5 days. So again, that traffic is not terminated by applying a restrictive security group.
So going further, just a quick note about Margarita Shotgun. And for those of you who are not aware, this is a tool that's widely used for remote memory collection in AWS, designed by folks over at Threat Response. And some of you may be asking, why haven't we leveraged this? But it doesn't really work for our use case because it requires SSH access into the affected instance, which doesn't really follow the principle of least privilege, as our team would need an SSH key for access to each production EC2 instance, which again, our risk appetite didn't really allow for. And in addition to that, we need to open port 22 to a particular IP address, which again increases, the potential attack surface area. So instead, we use AWS Systems Manager, SSM, which has an agent installed on each machine. And this agent is actually available by default on and installed by default on all Amazon Linux 2 AMIs. And we use this to remotely execute memory collection. So another quick note before we go further, I know we've talked about existing workflows and how ours is different. And our intention is definitely not to badmouth any existing workflows or tools. We just really wanted to explain to everyone why these workflows didn't specifically work for us. Requirements and therefore acceptable workflows, tooling, level of automation, etc., might vary for you and your organization depending on, your budget, risk appetite, and so on.
So moving forward, this is our memory collection step function. function. And we joke that, when you show something as simple as this to leadership, they're like, great, you can have it done in a week, right? But there's actually a lot going on behind the scenes. And we did run into some challenges, designing this memory collection workflow, more so than we did with disk. But at a high level, again, we are performing those checks, those dynamic checks to make sure we can collect memory without breaking anything. And if we can, then we go ahead and collect memory, we isolate the instance, and we suspend the instance and our state ends. If not, we really need to pause here and get business unit approval. Again, the business kind of comes first here. We want security to work with the business and not necessarily hinder the business if we can avoid it. So with that, Vaishnav is going to talk through some of the challenges that we ran into with memory collections.
So again, like with disk, we didn't want any intermediary storage if we could avoid it, and we avoid it by streaming the memory captured directly to S3. This allows us to not worry about either attaching a new volume to a production instance or hoping that one of the existing volumes has enough space to store the memory dump. And the way we really do this is Lime allows you to output the memory dump directly to standard output, and we redirect that standard output to an S3 API call, which allows us to stream that to S3 without storing anything on disk. The other thing we needed to keep in mind was to calculate the size of the memory dump before streaming to S3. Because if your S3 object that you're trying to push to S3 is larger than 50 gigabytes, you need to provide an expected size flag, or the put object API call will fail. So that's another thing that we needed to keep in mind. And then the last important flag to remember is the bucket owner full control flag. So by default, all our S3 buckets have a private ACL. What that means is it does not allow the bucket owner access to all objects in the bucket. It just allows the object owner, not the bucket owner. And this is important because we're hosting this S3 bucket in our security account, but we are creating the object from the monitored account because we're remotely acquiring memory from the production instance in a monitored account. So the bucket owner and the object owner aren't the same. So we need to add this bucket owner full control flag in order to allow us to later access the memory evidence for analysis.
So the second challenge that we've run into, and I'm sure you all have faced this as well if you've tried to collect and analyze memory of Linux instances, deals with the custom memory profile. So I'm sure a lot of you have used Lime before, but again, if you haven't, Lime's a great tool. It stands for Linux Memory Extractor, and we're using its loadable kernel module to collect volatile data from Linux EC2 instances. And again, this goes back to controlling specific AMIs that the end users can use within our environment. So not only do we have Lime on these instances, but we also have a cron job that compiles the Lime project upon reboot. And essentially what this does is it creates the kernel module that is needed to be inserted into the kernel to create the memory dump. And in order for volatility, again, our memory tool of choice, to parse through this memory dump, we need to create a memory profile. And to do this, we zip together the system map file along with the dwarf file, and this is all done on the fly upon reboot. And yeah, if you get this wrong, again, it makes it so much harder to analyze a Linux memory image, maybe even impossible with existing tools, unless you want to go through it with a debugger. But this can be a true pain. So our solution provides a custom memory profile to the analyst to ease this pain, and we upload it directly to S3 along with the full memory capture.
So ensuring network connectivity is very important. And again, we do not have direct control over the VPC used for memory capture, as opposed to, our disk workflow was completely controlled in our security account. But for memory capture, we're basically at the mercy of the production account and the VPC used. So where possible, we try to use S3 endpoints to stream memory to S3 over the AWS backbone network. But because this involves a change to the route table and with it a risk of affecting production workflows, this is a very tricky requirement to get around, where we necessitates a lot of dynamic checks and approvals on our end. However, for your specific work, use case, if your organization's risk appetite is higher than Goldman's, you could also stream memory over the public internet by adding a route to a NAT gateway or NAT instance or internet gateway, and stream, the memory capture to S3 over the public internet.
So again, we have some pro tips here, and these were just lessons we learned while going through the process. So the first one there is streaming directly to S3. That makes the process a lot easier, less to manage. Not a lot of tools will allow you to do this. So Lime was one that actually allowed us to stream standard out and standard air directly to S3. Just make sure to give the expected size flag if your output is going to be greater than 50 gigs. Otherwise, you'll run some headaches there. The next point is we wanted to consider business impact. So again, security teams are always, old-fashioned way of thinking. They're hindering the business. We don't want to do that moving forward. So we want to leverage whatever's there, whatever we can. So if we're going to make any dynamic changes using VPC endpoints, we want to make sure we're not disrupting anything. So that's when we do the dynamic checks. But again, yeah, if the VPC already had a NAT gateway, a NAT instance, or an internet gateway present, and you're comfortable streaming memory image over HTTPS, you can totally do that, and that works. We tested that in development, and that was really easy. And lastly, we wanted to know when you collect memory. And this is something we're still working out with the legal team, because collecting memory, is a little more complex or carries a little more risk than just collecting disk. And maybe you don't want to collect for every instance finding in Security Hub, but maybe you do. So something to consider there as well.
And then again, just to repeat this, gateway VPC endpoints require change to a route table in a subnet, and that could break a production workflow, which may or may not be worth it depending on the severity of the incident, as Ryan was saying. So it's very important to sort of have that categorization down and know when it is imperative to collect memory evidence and when you can just get away with disk. Another thing to keep in mind, so as we're baking these memory collection tools into every production AMI, it's imperative to implement some sort of file integrity monitoring on the folders that store these files, because they can easily be leveraged by an attacker for various nefarious purposes. Like, for example, if you have access to a memory dumping tool and collect a memory dump, you can then use that to dump passwords off the instance. So it's very important to have some file integrity monitoring in place. The other thing, this goes especially for Linux, we need to ensure that we can actually parse the memory image that we collected before suspending the instance, because once you do that, you lose all volatile evidence, right? So in order to do this, once we stream the evidence or the memory capture to S3, we spin up a container with volatility installed and use a custom memory profile that we created to just try to run some rudimentary commands like Linux pslist, netstat, etc., just to validate that we can parse the image and analyze it downstream.
So some closing thoughts here. So no solution's perfect, but this is version 1 of our solution here. And what's really cool is Vaisham and I come from a little bit of a purple teaming background. So we are now working with our security and incident response team to get them trained up on the output of our solution here and how they can submit things for manual input and manual review as well. So that's really important. And we're also taking their feedback as to what we can incorporate in version 2. But looking forward, a couple things we have on our plate. So as we alluded to earlier, we don't currently collect instance store data. It's not even really present in our environment, but we wanted to account for that too. So we're going to use DC3DD to stream that directly off the instance after we collected memory, and that would be done via an SSM document. And then, as Vaishnav just said too, right, we want to further leverage file integrity monitoring to restrict access to necessary tools. And that's easy for an attacker to abuse, but I mean, that may not even be the goal. So an end user could find this folder and be confused by what's going on here. Why is this on my AMI? They could delete it, they could move the folder, and that would break our SSM commands. So we need to really restrict that. And then the next point is actually really interesting. So we want to start to automate some of the basic analysis here. And our goal is not to automate anyone's job away, it's to make it a lot easier. So instead of having your analyst load the memory image and the volatility and then run through pslist, pstree, and wait for all of that to continue and complete, we want to have an automated workflow where we just output all of these commands to an S3 bucket, and then your analyst can jump on and actually do the critical thinking. They don't just have to press buttons.
So in future state, again, once we have our forensic analysis tools run on the evidence, our goal is to really analyze the tool output and look for risk factors and then assign a confidence score to the output. So for example, if our output of our disk forensic analysis shows some common indicators of compromise, let's say, TrickBot, Emotet, pick your favorite banking Trojan, this would increase the confidence score and show that the alert is a true positive and increases the temperature of the incident. We also want to basically generate a report with highlights of findings found. So for example, auto run keys modified, scheduled tasks created, cron jobs created, SSH RDP logins, pick your poison. And this is basically not to automate anyone's job away, as Ryan was saying, but sort of to facilitate the analyst that's actually performing the analysis to hit the ground running and get answers quickly.
So with that, we want to be conscious of time. The first thing we want to do is give a big shout out to the Bsides Knoxville organizers. You may not be aware, but even before this conference, a lot of stuff was going on behind the scenes to shift us to a virtual conference. They were meeting with every speaker, make sure we have connectivity checks and everything. And I think they did a really great job, really impressed with the conference. With that too, so Vaishnav and I will be active on Discord for the rest of the day. We've also included our Goldman email addresses there. First dot last name at gs.com. Feel free to connect with us on LinkedIn. If you're trying to build something similarly, you have questions, you're on the hiccups. I'm very active on LinkedIn, so it's Vaishnav. It's probably our main platform there. So please connect with us and reach out with any questions you have. And lastly, Twitter. Our handles are included there. It may be a little harder to type, but we're open on a lot of different sources. So with that, again, thanks for everyone for attending this talk kind of late on a Friday. We'll open up to questions now, or if you're more comfortable, post them in the Discord or write to us privately, and we'll be happy to answer them there. So thank you, everybody.
Thanks, everyone.
Thanks, guys. So we do have one question. Do we expect to see a public white paper, tech blog post, or something shareable like this?
Yeah, that's a great question. Version 1 was kind of getting the intro level talk out there, right? And even though we deep dived into a lot, you saw how this time really flew by. 50 minutes seemed like nothing. So yeah, our next thought is to kind of get it approved through Goldman. Again, we're kind of tied to what we can share in terms of exact code and everything. But in our free time, we're going to start to work towards more of a technical white paper.
All right, guys. And I know that we had a lot of people who wanted to see this talk. And as you already stated, just be active in Discord. I'm sure people will have a lot more questions for you.
Awesome. Yeah, I apologize that we can't share this, the deck, or have the talk recorded. We currently don't have any plans to share it elsewhere, but we will let you know too if that arises and if we do share this talk elsewhere.
Yeah, but again,
Excellent.
happy to answer any and all questions.
So thank you, everybody.
Thanks, everyone.
Thanks, James.
Welcome.